You know, it's been a while since I took beginner's chemistry, college chemistry 101, and I think I finally figured out, first of all, Argyria is all about redox. So if you want to get Argyria or get rid of Argyria, all you have to do is understand what does redox have to do with it, and then you know the whole story. So getting Argyria has to do with reduction of silver away from its oxidized state toward its metallic, simple metallic state, while oxidation is the opposite, takes you away from Argyria. Now, what does that mean electrically? This was the part that was difficult for me. Because logic, common sense, would dictate that sunbathing, which is one of the two ways you can get Argyria, is to sunbathe when your body is saturated with silver ions. The other is to consume vitamin C. Vitamin C is a known reducer, not only of silver peroxide, but a reducer of diatomic iodine. You know, the tincture of iodine stuff, Lugol solution, will render it into iodide. Vitamin C is very good at that. So if you get an iodine stain, just rub some vitamin C in it, a little water, a wet paper towel, and you'll reduce the brown stain to iodide, which is colorless. The iodine is still there, but it's colorless now. So sunlight hits a photovoltaic cell, contributing electric charge. So that's what it's doing to the skin. And if you have a silver there in the form of Argyria that you can see, or excuse me, if you have silver there in the form that you cannot see, it charges up the silver with an electric charge, right? Giving you Argyria. So if I'm oxidizing silver with hydrogen peroxide, which is the cure and the prevention of Argyria, then it stands to reason that the opposite of oxidation, reduction, is what sunlight does to silver and vitamin C does to silver, rendering peroxides of silver back into silver metal, giving you Argyria. And then the simple act of avoiding the sun and getting back into the tub, not every day, when you feel like it, and take a nice long soaking bath in silver hydroperoxide with MSM and some mineral salt of your choice. I choose baking soda, probably because it's the least likely compound to react with silver, to form a silver salt of its own. Bicarbonation is a very unstable acid. It bubbles out of solution very readily, right? So it's much better than any other kind of salt of sodium. And this way I get my sodium without encouraging Argyria. So by bleaching, literally, bleaching or oxidizing the silver in my skin, I reduce it back down, I oxidize it back up to its peroxide state, and it becomes invisible because it dissolves in body fluids. So what is electrically going on here? Well, with the help of a fellow, Machination 2 or you, Machination U or Machin, I can't remember or know how to pronounce his username on an energetic forum, but he gave me a hint because he talked about iron aluminum diodes. And then I looked up on YouTube, and I found a video on iron oxide and aluminum. And if you, what was the reaction, the chemical reaction he did? Cody something or other was the channel name. He oxidized the aluminum with the help of the iron oxide, but he also used heat. He used a blow torch. And so mixing the two powders together transferred the oxygen from the iron oxide to the aluminum. And that reminded me what goes on. The electricity goes in the opposite direction. And lo and behold, that's the polarity of a iron-aluminum diode. the aluminum side is negative, and the positive side is the iron. So when the two are joined together and react, I'm guessing they're using iron oxide for the iron. The oxide goes one way, and the electron flow goes in the opposite direction. So, what that means is that when we oxidize silver, we are removing some of its electric charge, but that doesn't sound right. Silver never had an electric charge to begin with. Idea time. It's the hydrogen peroxide that loses its electric charge. Why? Because it loses a hydrogen ion. And what floats with the hydrogen ion? The electron goes with it. Simple electrolysis, dude. Well, I never studied electrolysis, or if I did, I forgot about it. The hydrogen is an electron carrier. And it's taking away the electric charge, which tells us what we already know, that hydroxy radicals are bad for our health. Duh. Because the water lost its electric charge. Gave it up when it lost the hydrogen ion, rendering the basic water less life-giving. That's why lemon juice is so good for you, especially the liver, because it's so full of acid. It's full of electric charge, the hydrogen ions. So when we oxidize, it's not so much that we're oxidizing the silver. I mean, yeah, we are. But the reaction, the real action taking place, is on the hydrogen peroxide. Because that's fizzing, losing its hydrogen. And it's losing its electron charge at the same time. So, by losing the electric charge of hydrogen peroxide, we render it less oxidative potential, less potential to oxidize material, which also helps make it more stable, so it won't break down any further and turn back into water. It can't, because it lost a hydrogen ion, H2O2. Now it's HO2. It's not going to be that easy to get water out of that. But it would have been very easy to get water out of it had it kept its hydrogen ion. Because then it would have been H2O. But it would have had to lose an oxygen to do that. But you can't do that with silver. In order for silver to associate with hydrogen peroxide in a binding situation, chemical binding situation, the hydrogen peroxide has to lose one hydrogen atom, not one oxygen atom. So now it's not even related to water anymore. At least, not in simple terms. So, when the silver hydroperoxide is in solution underneath the skin, and then sunlight hits it, or vitamin C hits it, let's say sunlight. Sunlight hits it, what does it do? The photon carries an electric charge. A photon is an electron carrier, and it's carrying the electron charge to the oxidized silver, causing let's think a minute here. You know what? It's probably electrolyzing the water inside. It's probably electrolyzing water inside the flesh so that the water gives up its hydrogen charge, which can now displace the silver. And that new compound of pure hydrogen peroxide can soak up that electron charge. Meanwhile, you've got the hydroxy radical in the skin along with the silver particle, and the hydroxy radical is going to burn the flesh. No. Really? Like lye, sodium hydroxide. Is that what a burn is? An alkali burn? A sunburn is an alkali burn because the water was split by the sunlight into hydrogen and hydroxy radical? And the hydroxy radical burns the flesh? But then you're left with hydrogen, monoatomic hydrogen that's going to want to unite with other monoatomic hydrogen atoms to form H2, dihydrogen, stable molecules. Which is where that electron charge goes to. It goes with the hydrogen and gets soaked up in H2. So you're still left with the hydroxy radical burning the flesh. It's a chemical burn? Why not? You know, poison oak is a chemical burn. I found that out the hard way by having it. I quickly learned the nature of chemical burns. They're very different than a thermal burn. Your sunlight can't be a thermal burn. You never get hot enough. A thermal burn is when you take your finger and you stick it in the fire. That's a thermal burn. But a sunburn, it can't be a thermal burn unless the skin were to become so dehydrated, if you should become dehydrated, that the corpuscles of this flesh would shrink because there wouldn't be any space in there floated with water molecules. And that dehydrated state of low water content would overheat. You know, like a sidewalk covered with water versus a dry sidewalk is going to be hotter than a wet sidewalk because you got water evaporating, carrying away the heat. So dehydration could increase the likelihood of burn, and this has been the case in the case of electrical burns. I'm very prone to electrical burns from a zapper, like not a Hulda Clark zapper, that's too mild, a Soda Instruments zapper. Becker, you know, excuse me, not Becker, the other guy, Bob Beck. His AC-oriented zapper will burn my skin because I'm always dehydrated. It's very hard for me to hydrate, or gain weight for that matter, because the two are equivalent problems. So my ex-honey, who's younger than me and has very youthful flesh, would never burn, you know? And I'd burn in a matter of a few minutes. But that was an electrical burn, so that's a thermal burn because of the amperage. That's a thermal burn due to amperage and dehydration. But a sunburn is a voltage charge. It's not amperage. Even if you were grounded to this beach sand, you know, lying on it bare, you know, naked to the sand, without any insulation, no beach towel between you and the sand, and if the sand were moist, then it would still not constitute a thermal burn. There's no way. You don't get hot enough, and there's no amperage. So it's a chemical burn. Unbelievable. I'm just using logic here. I never bothered to think this thing through. It's a hydroxy radical, Li analogous, Lye, not Lie, Lye, as in why? Well, this is why. A Li burn, a caustic soda ash is sodium carbonate. A caustic sodium Li burn, because of the presence of the hydroxy radical, because the water was split by the sunlight, and the hydrogen and its electron, and that's why people sunbathe, because they get such a charge out of it, right? You get the electron carrier, the photon, full of electric charge hitting your body and giving you this rush. Meanwhile, you overdo it and burn yourself because you're so greedy. I want more charge. But all you had to do is hook yourself up to a zapper. If you really wanted that much direct electricity, you know. No, even better, a negative ion generator. A negative ion generator. Just hold the emitter and charge up your body with negative ion charge. There you go. And it doesn't burn you. I wonder why. Because, well, that is a very good question. Why doesn't it burn you? Oh my God. Oh, this is too much. why does a sunburn burn you, but being connected to a negative ion generator at 70,000 volts overnight while sleeping, which I've done several nights in a row, never burned me? Okay, so maybe it is an amperage burn. But where you have to ground out, you can't just be charged up. It's got to go somewhere. The amperage has to go somewhere. That electron, that hydrogen has to go somewhere. Oh, you exhale it. So how come the lungs don't get burned? Because, what? So dihydrogen is electrically neutral? Once it forms dihydrogen molecules, it should be electrically neutral. Which means the monoatomic hydrogen was not. But so what? It doesn't oh wait. Maybe it's not neutral. Wait a minute. Maybe it is through the breath. But why wouldn't you sear your lungs, though? You know, the dihydrogen might be neutral, but it still carries away the charge. So it does not burn the lung tissue, yet you lose the electric charge that you had. Because now, even if it didn't form dihydrogen molecules, it would still want to leave the bloodstream through exhalation. And no. But if it was dinitrogen, it wouldn't burn I would presume, speculate that it would not burn the lung tissue. So your lung tissue would be saved, your skin would... No, that doesn't make sense. Oh, shoot. You know what I think? There's something in the flesh that's causing the burn. It's not the hydroxy radical. It's the sodium ion. Why? Because the bicarbonation in the bloodstream gets charged. And what would happen? Because normally it's buffered with sodium ions, sodium bicarbonate. If it gets an extra charge from the split water molecule, it'll get an extra hydrogen ion, that's right. Which means the sodium ion will be left all by itself, but the H2CO3 will have to leave solution. And so sunbathing forces the debicarbonation of the bloodstream, the eradication, the cleansing of the bloodstream of the very waste elimination that the body is trying to get rid of, the bicarbonation molecule. It cleanses the bloodstream of that, as well as charge up the body in the same time. So you're getting two things happen. You're getting an electrical charge, and you're flushing your bloodstream of bicarbonation, reducing the quantity of bicarbonation in the bloodstream, which would be a lift because carbon dioxide is what suffocates us. Without getting more oxygen, it makes it appear that you're getting an oxygen rush. You know, kind of like, what's-his-face, Michael Jackson sleeping under a hyperbaric chamber. He was getting oxygen forced into him, while sunbathing does the equivalent thing without giving you extra oxygen, by simply eliminating the bicarbonation in the bloodstream. So that's why your lung tissue doesn't burn. Not because the hydrogen forms dihydrogen molecules, but because it unites with the bicarbonation in the bloodstream. Okay, so now you have hydroxy radicals in the skin, and you have sodium ions in the bloodstream not paired off with bicarbonation in the bloodstream. So now the sodium matches up with the sodium hydroxide, and now you've got a sodium lye chemical burn, for sure. For sure. So it still goes back to chemistry. It's not a thermal burn. Wow. You see what reasoning can do? If you reason adroitly, let's hope that's adroit, accurate, in other words. Sounds accurate to me. So how did I start this video? I forgot already. Oh yes, the definition of Argyria and its cure is redox. See, redox solves or explains a lot of riddles, a lot of mysteries, and Argyria is one of them. So now you know why all those vitamin supplements, selenium, vitamin E, is supposed to take care of Argyria. Well, you know what one of those 6 vitamins were in that recipe for getting rid of Argyria? Was vitamin C. Yeah, reduce the silver. Duh. You know. Oh, it just hit me. Yeah, the bullet hit. No. The silver bullet hit you. Now I get it. But I'm not a wolf man. Well, I don't know, maybe. Yeah, reduction of silver with the help of vitamin C. Along with all the other antioxidants, the vitamin E. So an antioxidant is a reducer. Antioxidant. Duh. So hydrogen peroxide is an antioxidant? Wait a minute now. No. The vitamin C is not acting on the silver. It's acting on us. Our body fluid. And it's the body fluid that oxidizes the silver. Of course. So it's a complicated roundabout fashion of doing what hydrogen peroxide does. Taking all those vitamins. Let's see if I can remember all 6 of them. Vitamin E, selenium, vitamin C, MSM, kelp. Was it 5 or 6? No, it was 5. I added a 6th one, cayenne pepper. That's right. Speculation on my part. No, it was 5. Vitamin E, vitamin C, selenium, MSM, and kelp, sea kelp. Those were the 5 vitamins, megavitamins. Oh no, there was a 6th one, B complex. That's right, B complex. Then I added the 7th one, cayenne pepper. That was it. So those 6 vitamins, megadosed, is supposed to oxidize the silver. That makes no sense. Vitamin C is an antioxidant? What? Vitamin E is an antioxidant? What? To get rid of Argyria, you have to oxidize it. Maybe not. There's one other route you can take, and that is to turn silver into an ion salt. A silver salt. Which is highly unstable. Can fall back into Argyria readily enough if it were not for the MSM and the sea kelp containing algin to bind with the silver. Possibly provided that the silver is an ion. So without having to go through the oxidation of the silver, Argyria is eliminated because the silver is turned into an anion, a positive ion of silver, which is quite a feat. But I can do the same thing with a sleep circuit. 6.6 gigaohms of resistance hooked up to a AA 1.5 volt battery, and sleep in it, and the the moderate voltage of 1.5 volts and the suppressed amperage of 200 picoamps will also flush out most of the Argyria in the body, depending on where you put the contact points too. I mean, if you have Argyria that's spotty, you can always put the contact point right over the spot where the flow well, the charge, not the flow. There's no flow because it's suppressed amperage. So you put the lead over the Argyria so that the voltage charge is most concentrated, because it's the voltage that's going to eliminate the Argyria. So apparently those 6 vitamins beefs up the voltage charge of the body, which is not a bad thing, you know. Electrostatic charge, good for life, life-giving, vitality. Cool. Yeah, isn't it cool to figure these things out? Yeah, it's just so cool.